In the previous lecture, we looked at the design of our reactor systems, and we developed our design equations in the face of a variable temperature, a temperature that might respond to the reaction rate. So in the current section, we are extending that to consider the case of reactions that might be reversible. So if we have a reversible reaction rate, then we will have a specific relationship between the conversion and the temperature, and we wish to pick our design variable such that we can optimize the size and the operation of our reactors. So if we consider this reversible reaction A and B, with these being elementary reactions, then the forward rate of reaction A going to B we'll write as R1 K1Ca, and then the reverse reaction rate will be B translating back to A, so that's R2 is K2Cb. And then, of course, the net rate of reaction will be R1 minus R2, which is K1Ca minus K2Cb. And then if we group out a K1 here, we can write this as Ca minus Cb. And then we will define Ke to be K1 over K2. So if we group out K1, this is K2 over K1, so that's Cb over Ke over there. So that's the development that we can write in terms of the net rate of reaction. So we can define little r to be the net rate of consumption of A. And in this example that's shown, we've specified the kinetic rate constants here. So K1 and K2, we've got the pre-exponential factors and the activation energies given. And so our question here asks us to determine the forward, reverse, and net rate of reaction if we have a temperature and we have a fixed conversion of 0.5. So we can view the results here. You can see the net rate of reaction over there, and then the rate at which A is being consumed is shown here. And note that this is a plot of just RA. So of course, the consumption is a negative number, and then the production of A due to B transforming back to A is a positive number. So on balance, this is a positive production of A. So if we have the situation of a conversion of 0.5 under these temperatures, we can see on balance we will be producing A rather than converting A to B. So of course, we could also say both reaction rates are increasing with temperature. Well, in this case, it's becoming more negative, but the actual reaction is increasing. So both rates are increasing with temperature, but the net reaction rate may increase or decrease depending on which rate increases more. So we want to use this, or we want to design our reactors in the face of this additional complexity. So let's consider first where the equilibrium might lie. So of course, equilibrium will be where the two reaction rates are equal. So R1 equals R2. And then let's work over here. So we have that R1 equals KCA, and R2 equals, and that should be K1. And so R2 is KCB. And we can rewrite this as K1 Ca naught times 1 minus the conversion, and Cb, if we assume component B is not in the system initially, then the only time we will have component B is when A is converted to B. So this is simply K2 Ca naught X. And then we can write in terms of our net reaction rate, we can say R equals R1 minus R2 equals K1 Ca naught times 1 minus X minus K2 Ca naught X. And of course, we can group out for K1 Ca naught and rewrite this as 1 minus X here. So 1 minus X. And then if we group out for the equilibrium constant, then this becomes minus X over Ke. So that's a relationship that we have between R and X. So we can regroup this also. We can say this is K1 Ca naught times 1 minus X into 1 plus 1 over Ke. So we can rewrite all of this in terms of K Ca naught. And so we can see here that at equilibrium, if we require R equals 0, then we can say these two are simply equal. So let's write that here. We can say at equilibrium, so this was the general case when R is not 0, but at equilibrium, we have R equals 0, implying R1 equals R2. So R1 and R2, we've got K1 Ca naught 1 minus X equal to K2 Ca naught times X. And so we can cancel these Ca naughts, and then we can divide through by K2. So we can write this as Ke 1 minus X equals X. Or we could group out the x's and rewrite this as x into 1, and then this is going to be a minus Ke, and then take across, and it's a plus Ke equal to Ke. So we can say here x equals Ke over 1 plus Ke. And of course, Ke is a known function in temperature, because Ke we define to be K1 over K2, and both these are known functions in temperature. So we have the Arrhenius relationships for K1 and K2 in each case. So we can say K, or rather X, is a known function of temperature then. And of course, this relationship comes from the assumption of equilibrium. So at equilibrium, there is a specific relationship between temperature and conversion, which is this one. So let's just be a bit more specific in the way we write these equations. Let's write these in as equilibrium conversions. So this is the equilibrium dependence on the temperature. And if we take our example, right, if we take the example that we introduced just now, we can draw that equilibrium out. So we can draw out the conversion as it varies with temperature, and it's this line. So you see it's not linear, it's a ratio of these exponential functions. So we know behind these are exponential functions. In here we've got exponentials for the Arrhenius. And then in Arrhenius, of course, it's a dependence in minus 1 over t. And then we've got a 1 plus here. So we can see this is a fairly nonlinear equation. And it looks like this. Now, of course, it's useful to know where the equilibrium lies. And in fact, we often want to know that because that's the point that we wish to avoid, right? We don't want to operate near equilibrium because, as we've established, that's the point at which the net reaction rate is 0. So we actually do want to stay away from this line. And so we are going to look for designs that stay as far away from this equilibrium line as possible. And even so, even though we know it's the region to avoid, we can still then say, well, it is a useful thing to know. We do need to know what region we need to avoid. But it's not always the case that we can get this equilibrium line so easily. Because you see, for us to predict it, we do need to know K1 and K2 as temperature functions. And that means we have to know our kinetics quite exhaustively. We have to have the temperature relationships. And so we would like to avoid that as far as possible. We would like to know is there some simpler way of predicting the equilibrium line? So to obtain our equilibrium relationship, we need this equilibrium constants temperature dependence. And we do have available to us the Van 't Hoff equation. So the Van 't Hoff equation gives us the relationship between the derivative in temperature of the natural log of the equilibrium constant, that being equal to the ratio of the heat of reaction to the universal gas constant and the temperature squared. So this relationship is available to us from thermodynamics, and we can rewrite this heat of reaction in terms of the standard heat of reaction. So this is the heat of reaction at some specific reference temperature, TR. So that heat of reaction plus the contribution due to temperature difference here. So that's the delta heat capacity. So remember, delta heat capacity is the ratio of the stoichiometric coefficients multiplied with the individual heat capacities. So that gives us a delta Cp. So this is all dependent on the reaction. So the specific reaction will give us the stoichiometric coefficients, and then we can evaluate delta Cp. So we've got the delta Cp here, and that's multiplied with this difference in T minus Tr. So if we want to integrate this, looking at the left-hand side first, of course, this is a derivative in temperature. And if we integrate this between the limits T1 to T, then of course, we take the function itself and take the difference of that function in T1 and T. So ln of Ke at T minus ln of Ke at T1, the difference of those natural logs we can combine into the ratio of the arguments of those two terms. So that's the integral on the left-hand side. And then on the right-hand side, we can consider these two terms. Well, we have two functions in temperature here. So there's a temperature function and there's another temperature function. So let's look at this as the integral of, and if we just integrate this function in t squared first, then of course the integral of 1 over t squared is minus 1 over t. And so if we are integrating from t1 to t, then we would write this as 1 over t minus 1 over t1, and then we can just reverse those to get rid of the minus sign. So that's the one term. And then if you look at the other term, we've got a t over here, and it's going to be a t, and then there's a t squared in the denominator. So if we integrate this part, then we've got this contribution here. So that's the integration. That's what integration gives us for equation 10. And of course, we can then use this relationship to get the equilibrium constant as a function of temperature. And so what's nice about this equation is we only need to know the equilibrium constant at one specific temperature, and we only need the enthalpies of our species thereafter. So the enthalpies, we generally have the sense that we can get these functions as we can get these as functions of temperature. So that's all nicely tabulated from the decades of measurements that are behind each of these species. So we should generally feel that although this is not a linear function, we can get values for each of these things, and we can evaluate this. And then we just need one equilibrium value here, and we can use this equation to find the equilibrium value for any temperature. So what's nice here is we don't need the reaction kinetics for this reaction anymore. We do need to know what the reaction is, of course, so we need those stoichiometric coefficients, but we don't need the rate expressions. We can evaluate the equilibrium temperature like this. And then, as we mentioned also, if we do just have the Arrhenius constants, we can also get it this way. What's interesting also is to try and compare the two results. So we do have this result available to us from the Van 't Hoff equation, and then using the relationships, the Arrhenius relationships, and this, we can say, well, then this must equal this. Well, if we take exponents on both sides. So if we do that, you can see here that for the simplifying case of delta Cp being 0, that when you compare these two equations, that the heat of reaction will be in the position where we have E1 minus E2. So the heat of reaction is equal to E1 minus E2 for the case where delta Cp is approximately 0. So this is a useful thing to have in that if we are given the kinetic rate constants as temperature functions, then we could just compare E1 and E2 to determine whether this is going to be an exothermic or endothermic reaction. So if E1 is more than E2, then this will be positive and it's endothermic, and if E2 is greater, it's exothermic, and that's useful to know. All right, so if we continue with this example, we've got this equilibrium line, and of course, we would like to evaluate the reaction rate at other positions as well, because that's actually where we are getting some of A being converted to B. So we can go back to our original formulation here. So we had established this expression for the reaction rate, the net reaction rate. So we now have Ke as a temperature function, and we have x as a variable. So we could simply plot these lines out now. And we're going to plot them in a special way. We're going to plot them as isorate lines. So we are going to say, let's take the plane of conversions plotted on the y-axis and temperature plotted on the x-axis, and let's pick specific values for reaction rate. So if we pick a value for the reaction rate, then we are specifying a constant here, and then we are considering a range of temperatures. So if we let the temperature vary, then Ke is going to vary, and then we can solve this equation for x. So because we've fixed a value for r and we are fixing values, a set of values for t, then that fixes a set of values there. And then, of course, we are doing all of this for some fixed concentration. This is also a temperature function, by the way, so we need to preserve that. But that's a known temperature function. So the only thing left over is this x. So we can construct the locus of points which describe an isorate line. So we fix a reaction rate and we calculate for a range of temperatures the values of conversion that we might have. So like this, you can see a family of curves that we can consider using for our design. And it's important to note here that this is all for a specific reaction type, but it says nothing about the type of mixing or the reaction arrangement. It's not saying anything about the reactor itself. So this is purely about kinetics. In other words, this is telling us only about how nature is behaving. So these lines are what nature gives us. So nature tends, if we achieve a certain conversion, if we have a specific conversion in the reactor, which means we have a specific concentration of A and a specific concentration of B, and if we have a specific temperature, then those components will react at some specific rate. So A and B will, the forward reaction and the reverse reaction will be specific values. So first, we read a conversion as a specific concentration set, and then there's a specific temperature, and those two together fix a specific reaction rate. So that's what we've learned. You can say we've learned from nature that this is the reaction, the net reaction rate. And now, of course, we want to come along with our little reactors, and we want to navigate our way around this plane so that we can achieve high reaction rates and a good conversion, and doing all of that in an economically feasible way, which means producing reactors that that have a reasonable volume and all those good things. So if we go then into our well, in the notes here, we go into a few more observations. So this is the same as the derivation that I presented earlier. It's grouped out in a neater way. So we've grouped out for x over here. So this is a nice, easy way to produce our plot. So if you take this equation, you can see that this is the same as this one. It's the same as this equation, and then we can group out for x like this. And so we can fix a temperature. So given any temperature, we can look up the values for K1 and K2. And then if we are trying to plot a specific isorate line, then we'll know what value of R to use here as well. And we use the fixed concentration, and so that gives us our conversion. So that's how we can generate those lines. And of course, the equilibrium, you can say, is just a special case of this line. So the equilibrium line is simply where this RA is a 0. Right, so that's how we can get that plot. And now we want to come in with our reactor design. And let's just go back to our previous development. So so let's go back to this relationship. So we said in this relationship, this was the heat added, and that's the shaft work, and then this is the interplay between the conversion of our components, and so the internal energy and the thermal energy given off. This is really where the reaction is operating. So let's say we operate our reactor, and we haven't specified what reactors yet. Let's say we operate that reactor adiabatically. In other words, we don't add heat to the system, so we ignore that. And let's say we don't do shaft work either. So those two can vanish, leaving us with just these two terms. And of course, we can cancel off these FA naughts then, leaving us with this relationship in T and X. We've got this relationship. So if you take that same equation and those two terms, we can rewrite it like this. So directly from the energy balance on our reactor, we have this relationship, and this is for an adiabatic system. So we aren't adding heat or shaft work. So this is the relationship between conversion and temperature. So basically, we can read this equation as that if we have achieved a particular temperature in that reactor, given that we had fed the reaction mixture at T in, then we must have achieved a conversion of X. So once more, if we aren't adding heat or shaft work to the system, if our temperature changes from the inlet, so if it goes from T in to T, then we must have converted this amount X. So this is a nice line that we can draw on our isorate plot. So if we go back to this one, let's just move that over to our screen here. So let's just put this down, and let's draw an isorate line then. And let's just think about this isorate line first. So if you look at the form of this equation, you can see the heat of reaction minus heat of reaction down here. So this is heat of reaction at the reference temperature. So we are assuming that the heat of reaction doesn't change that much over the temperature range that we are considering. Now you can see it's a minus heat of reaction here. If you look up here, these are all positive numbers. So the reaction, the heat capacity, Cp, these are all positive numbers. And this is the inlet molar flow ratio. So we can't have negative numbers for inlet molar flow ratio. So this is all positive. And then if you look here, this is T minus T in. And of course, we don't know what these signs are. But we can say that if we were to look at dx dt, that we can decide on the sign of this. So if we take dx dt, then the equation looks like sum beta I CPI over minus heat of reaction. And then, of course, in taking dx dt, this is going to vanish. So that's a constant. And then we are differentiating in t. So that's dx dt. And you can see here for an exothermic reaction, this is going to be a negative number. And so it's minus minus. And we said that all these are positive numbers. So this is on balance going to be a positive number for an exothermic reaction. So dx dt is going to be positive in the case of an exothermic reaction. And of course, the reverse is true, that if this is an endothermic reaction, then this is going to be a positive number. So this is on balance going to be a negative number. So the slope will be negative for endothermic. So in this case, this line was plotted for an exothermic reaction. So remember when we said earlier that the heat of reaction is E1 minus E2. So here we can see E1 is 30,000 and E2 is 41 something thousand. So E1 minus E2 is negative. So this is an exothermic reaction, which means for the operating line dx dt, we are going to have a positive slope. So our operating line for the reactor is going to look something like this. And we do expect this because if we start down here, so where conversion is 0, that means the concentration of A is high, then the net reaction rate is non-zero here. And you can see the line is pointing in this direction. So it is going to tend to equilibrium. So we know that our chemically reacting system is trying to move to equilibrium. So we expect this line to be positive and sloping and moving in this direction as it is. So let's take an example in plotting one of these lines. And you'll find example 2 in the notes. And as usual, we've got these Arrhenius relationships defined for us. So that's quite convenient, all the constants defined nicely. And we are told the reaction mixture is pure A entering at 250 Kelvin, and the product is leaving at 320. So if nothing is given to us in terms of the heating and cooling of the system, perhaps we can assume that this is an adiabatic system. So if it's adiabatic, then of course this relationship applies. And let's just write that out here. So we've got x equals the sum beta I in CPI over minus heat of reaction, and then T minus T in. And let's look at plotting this line. Now, if we look at this question, it says that we have pure A entering the reactor. So just a quick sketch of a reactor here. So the feed stream is only A, and so we can say beta A, well, of course, by definition, beta A is a 1, and the other component to add, of course, is component B. But if it's pure A entering, then beta B is, of course, 0. And if we had an inert, then, of course, we should add that also. But the question doesn't mention any inert. It's just pure A entering. So there's only a beta A term in this equation. So we could say simply that this is x equals beta A times CPA. And we could say plus beta B CPB, but beta B is 0. So there's no point to writing that in. And then divided by minus heat of reaction, and of course T minus T in here. And if we look at this equation, it's really easy to draw the line for this, because theta A is a known thing. And in fact, there's additional information in this question. So we've got the heat capacity of component A here, and we don't even need this heat capacity of component B. So it is given, but it turns out we don't need it for this equation. And of course, we do need the heat of reaction. But if we look here, we can recall the relationship that we have available to us. So we said delta heat of reaction is approximately the same as E1 minus E2. E2. So we can just take 30,000 minus 53,520, and that's our heat of reaction. So that's known also. And of course, T is the variable, and then we do have the inlet temperature specified. So that was 250 Kelvin. So everything is defined for us in this equation, and we can just plot that out then. And here it is. So we've plotted this line. So it's starting out at 250, and we've, of course, we can say that we can take the slope of this line. So dx dt is simply sum beta I CPI over heat of reaction. And that sum beta I CPI is simply CPA, and that is known. So we get the gradient quite easily that way. So we've got a starting point. We know that if we are entering with pure A, then the conversion is 0. So we've got 0, and we know the temperature is 250. So that defines this one point. So we've got a point, and we've got a slope. So we can say, basically, as the system reacts, it's going to move along this line, and with the end goal, of course, being here at the equilibrium. We can't cross equilibrium. We can't even land on equilibrium. It takes an infinite period of time or an infinitely large reactor to get there. But anyway, we are moving along this line. So that we can think of that line in the context of this plane as being our human attempt to achieve some kind of conversion. And this plane of this equilibrium line and these isorate lines, that's what nature is doing. So nature says, okay, if you are here, then this is what I'm going to do to you. So if you are here, then I'm going to react to you at a certain rate. And you can see that rate varies along this line. So although it looks like a nice straight line, if you start out here, then you can see the reaction rate is between 10 to the minus 7 and 10 to the minus 8. And as you increase along this line, you can see the reaction rate actually goes up around here. So here the reaction rate is somewhere between 10 to the minus 6 and 10 to the minus 7. And then here it's very close to 10 to the minus 7. So reaction rate is varying along this line. And where we choose to stop on this line basically defines our design. So if we say, okay, I want to stop here, I want my exit temperature to be 300, then that defines a specific reaction rate. So if we pick this point, right, at least we know this line now. So if we pick a point here, that defines a temperature and a conversion. So we can use this plot and look up those two values. So we can say X and T are now known. Well, they are designed, right? So we pick values X and T, and we can then determine the volume required for that reactor. So if we go to our isothermal reactor design equations, then simply our CSTR, if it's a CSTR, let's say, that we are designing, our single CSTR, we have this form. So we had said, let's stop somewhere around 300. So the temperature here was, we picked 300, and we picked, if we pick 300, then that gives us something like 0.22 for X. So 0.22. So we can use that with our design equation, and so we can use 300. So behind this RA, of course, we evaluate K1 CA minus K2 CB, and we make the substitution for RA over there. Well, let's do it. So we've got V equals FA in XA, and we've got RA, and RA is K1CA, and we know CA is CA naught 1 minus X minus K2CB. So CB is CA naught X. We're using XA here, so we should say XA and XA. And of course, we have the Arrhenius relationships for K1 and K2. So we can substitute X is 0.22 here, here, and here. CA naught is known. So we know the inlet concentration of A, and then T is known. So we can evaluate K1 and K2 for a temperature of 300 Kelvin. So that's known, and then that's known. So everything is known here, and we can calculate the volume. And maybe let's rewrite this in this form. So V equals FA in XA over RA. You see here, when RA is bigger, right? So when the reaction rate, when the net rate of consumption of A is large, then to achieve a fixed conversion, we need a small reactor volume, right? So once more, if this is a large number and this is a fixed number, then this is a small number. So in other words, we only need a small reactor if the reaction rate is nice and high. And of course, as the reaction rate drops, then to achieve that same conversion, the volume must be much greater. So that is a concern for us. So as we are moving along this line, the reaction rate is changing. And so somewhere along the line, there exists some best choice, right? So that's something of interest to us that we need to think about. Also, of major concern to us is the fact that we seem to be constrained here. We said we can't cross equilibrium, and yet the highest conversion we can achieve in this case is only 30%. So we have to think about some way to enjoy a much higher conversion. We'd like to be somewhere up here because that means we've got a nice high concentration of product, whereas this reaction seems to be limiting us down here. So we have to think of some strategies for doing that, and that will be the subject of the next lecture.